Let us start exercise 1.2 of NCERT CBSE class 10th. Exercise 1.2. Here express each number as a product of its prime factor. So the number is given 140. Its prime factor will be 2 into 2 into 5 into 7, and it can be also written in the form of 2 raised to power 2 into 5 into 7. Second question is 156. If you factorize it, you will get 2 into 2, 3 into 13, and it can be further written 2 raised to power 2 into 3 into 13. This will be the answer. Now, third part, that is 3825. It can be also factorized 5 into 5, 3 into 3 into 17. And that can be written like this: 3 square into 5 square into 17. This will be the answer. Now the next question, next part, that is fourth part, is 5005. So 5 into 1001 it will be equal to 5 into 7 into 11 into 13. This will be the prime factors of 5005, and this will be the answer. Now the next part, that is fifth part, 7429. So it can be also factorized 17 into 19 into 23. In this way we have finished the question number 1. Now proceed to the question number 2. Find the LCM and HCF of the following pairs of integers and verify that LCM into HCF equal to product of the two numbers. You see, the two numbers are 26 and 91 in the first part. So 26 can be written like this: 13 into 2, and 91 can be written as 13 into 7. Therefore, the HCF will be 13 because 13 and 13 both are present there. So the intersection of the factors, that is 13 here. And if you have to find out the LCM, so for LCM, what we will have to do? We will have to take all types of factors present in both, but from where we can get maximum, that will be taken. Here you see 13, 1, 2, we can get only 1 from anywhere, and 7. So in this way, 13 into 2 into 7 will be equal to 182. Now let us verify. You see, HCF into LCM will be equal to 2366. Here the numbers 26 into 91, the product of the number, that will be also 2366. Hence it is verified. Now let us start the second part, that is 510 and 92. 510 can be factorized 2 into 3 into 5 into 17, and 92 can be factorized 2 into 2 into 23. So the HCF will be 2 because only the factor 2 is present in both the numbers. And for LCM, you see, we have to take the maximum number of the factors which is present somewhere. You see, here 2 is present 2 times. Here 3 is present only 1 times. So I have taken the maximum number of 2, 3, I have taken 5. So all types of factors should be present in the LCM, and it should be in maximum number. So I have taken only these 2, 3 from first one, 5, 17 and 23. Multiplied it, we got 23,460. Now if you multiply HCF into LCM, we will get 46,920. And if you just multiply the product, that is 510 into 92, we will get 46,920. Hence it is verified that it is also correct. Now come to the third part, that is number is 336 and 54. 54 can be factorized. 2 into 3 power 3 and 336 can be factorized 2 raised to power 4 into 3 into 7. For HCF we have to see the intersection of the factor, we can say, or which is common, which we can take from both. That particular, you see, we can take 2. We can get 2 from both the numbers and 3 from both the numbers. So HCF will be equal to 2 into 3, that will be 6. For LCM, you see, maximum number of 2 which we can get from this place. So I have written 2 raised to power 4, and maximum number of 3 we can obtain from this place. Now maximum number of 7, we can only got 7 here. So 2 raised to power 4 into 3 raised to power 3 into 7, that will be equal to 3024. Now you see, HCF into LCM will be equal to 18,144. And if you just multiply the number, product of the numbers, that is 336 into 54, it will be also equal to 18,144. Hence it is verified that it is also correct. Find the LCM and HCF of the following integers by applying the prime factorization method. You see, the numbers are 12, 15, 21. First of all, I have just factorized, prime factorization is there. 2 raised to power 2 into 3, 15, that is 3 into 5, 21, that is 3 into 7. So HCF will be, you see, only we can get 3 from each, we can get 3. So 3 is common factor. That is why I have written the HCF is 3. For LCM, you see, how many 2 we can get? Maximum number of 2, that is 2 raised to power 2. How many 3 we can get? From anyone, maximum number from anyone. So only we can get only 1 3 from this place, so only 1 3 will be taken. Now you see 5. So 5 is also there. 7 is there. So just multiply it, you will get 420. This will be the LCM. For second part, 17, factorize it 17 into 1 because it is a prime factor, prime number. 23, it is also a prime number. 29, it is also a prime number. Therefore, the HCF will be 1. All prime numbers are co-primes. Now the LCM, that will be equal to 17 into 23 into 29. This will be equal to 11,339. Now third part of the question number 3, that is 8, 9 and 25. 8 can be factorized 2 raised to power 3. 9 can be factorized 3 raised to power 2. 25 can be factorized 5 raised to power 2. So HCF is equal to 1. LCM is equal to 2 raised to power 3. 3 raised to power 2 into 5 raised to power 2. That will be equal to 1,800. So this will be the answer. Now proceed to the question number 4. Given that HCF of 306 and 657 is 9, find the LCM of 306 and 657. So you see, the LCM will be equal to the product of the numbers. I have taken the product of the number divided by the HCF. So 306 and 657 divided by the HCF, that is 9. So You will get, you see, I have just cancelled it, by it will come 34, so 34 multiplied by 657. It will be equal to 22,338. Question number 5. Check whether 6 raised to power n can end with the digit 0 for any natural number n. You see, if you just factorize 6 raised to power n, so 2 into 3 whole raised to power n, that can be written in the form of 2 raised to power n and 3 raised to power n. If a number ends with 0, prime factor must be 2 into 5. Means 2 into 5 should be also one of the factor, but 2 into 5 because 2 into 5 is equal to 10, where 6 raised to power n can be factorized in only 2 into 3. So 6 raised to power n cannot be end with the digit 0 because its prime factor do not have pair of 2 into 5. Now question number 6. Explain why 7 into 1, 11 into 13 plus 13 and 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5 are composite number. You see, first of all, I have taken the first one number, that is 7 into 11 into 13 plus 13. So I have taken 13 common. So we are left inside the bracket, that is 7 into 11 plus 1. If you solve it, you will get 13 into 78 is equal to 13 into 13 into 2 into 3. Now next you see 1001 plus 30, that will be equal to 1014. You see, just if you add all these things and solve it, you will get this number. So 13 into 13 into 2 into 3. So 1014 is a composite number because it contains more than 2 factors such as 1, 2, 3, 6, 13, 26, 39. These are the factor, and number itself is also a factor. So it has got more than 2 factor. That is essential for being a composite number. At least there should be 3 factor, but it has got more than 3 factors. Now the second part. 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5. You see, I have taken 5 common. So 7 into 6 into 4 into 3 into 2 into 1 plus 1. So if you just solve it, you will get 1008 plus 1. That will be equal to 1009. In this side, if you just solve it, you will get number 5045. Here you will get 5045. So these are the factors. And I have written the factor like this. 5045 will be equal to 1 into 5 into 1009. It also contains more than 2 factors. Therefore, it is a composite number. Now proceed to the question number 7 of exercise 1.2, that is, there is a circular path around a sport field. Sonia takes 18 minutes to drive one round of the field, while Ravi takes 12 minutes for the same. Suppose they both start at the same point and at the same time and go in the same direction. After how many minutes will they meet again at the starting point? So this question can be solved by taking the, you see, this is the starting point. Sonia takes 18 minutes, Ravi takes 12 minutes to move in a particular direction. So starting time is the same, starting point is the same. So what we'll do, that we'll take the LCM of 12 and 18. You see, 12 has been prime factorization, that is 2 raised to power 2 into 3. 18, that is 2 into 3 raised to power 2. So LCM will be equal to 2 raised to power 2 into 3 raised to power 2, that will be equal to 36 minutes. So after 36 minutes they will meet. And if you want to know the next one, you just take the multiples of 36. In this way, we have completed the exercise 1.2. Now proceed to the exercise 1.3. We have to prove here that root 5 is irrational. 1.3, prove that root 5 is irrational numbers. The proof. In such a proof, I have taken some steps so that you can easily memorize it. First of all, what we will do, that we take the contradict. Contradict means just opposite what we have to prove. We have to prove that it is a irrational number. Let us proceed that it is a rational number. So let us assume to the contrary that root 5 is rational number. Now in the second step I have written if root 5 is a rational number, the rational number as per the definition, rational number can be expressed in the form of p by q, where q is not equal to 0 and p and q are both integers. So root 5 must be equal to r by s. Suppose in case r and s are not co-prime at that time, they may have common factor. For example, let it have common factor h other than 1. So r can be expressed into a into h and s can be expressed as b into h, where h is the HCF of r and s. If it had not been HCF, then we have to again simplify it. And if you are just having the HCF, it means that will be the simplest form. So the root 5 will be equal to a into h upon b into h, and h cancel. So the root 5 will be equal to a by b. Now a by b is the simplest form, where a and b are co-prime, means the HCF of a and b is 1. So just cross multiply it, we will get b root 5 equal to a. Now squaring in the fourth step, squaring both sides we have. So if you just square it, the root will be removed. So 5b square. On the right hand side we will get a square. Now you see, a square is the product of 5 and b square, means 5 is also a factor of a square. 5 is a factor of a square. Therefore the 5 divides a square. And 5 is a prime number. If any prime number divides the square of any number, means the 5 will divide the number itself. So the 5 divides a. 5 divides a. This will be also, further you can consult the fundamental theorem of arithmetic. The square of any number is divided by any prime factor. That prime factor also divides the number. You can take the example like 36. Suppose 36. Now 36 can be divided by 2 or 3. These are the prime factors. So the 2 and 3 will also divide 6. The square root of the 36 is 6. So the 2 and 3 both will divide 6. Here also you see 5 divides a square. Therefore the 5 divides a. And this is the fundamental theorem of arithmetic. Now step 5. You see, once 5 divides a, it means there would be any integer, let that integer is c. So a is equal to 5 into c. Now squaring, So a square will be equal to 25c square. So here you see the 5b square. 5b square is equal to a square, and a square is equal to 25c square. So you can write 5b square is equal to 25c square. It means that b square is equal to 5c square. You see, 5 and 25 has been cancelled, and we have got b square is equal to 5c square. Now you see the 5 divides b square. 5 divides b square. 5 divides b also. If it divides the b square, it will divide the number, means the b. So b will be also divided by 5. It is according to the fundamental theorem of arithmetic. Now step 6. From step 4 and step 5, 5 divides a and b. Hence 5 is a common factor of a and b. But this contradicts the fact that a and b are co-prime. Step number 3, you see, step number 3 we have mentioned here where a and b are co-prime. But here we are saying that 5 divides a and b. Means once we have said that these are the co-prime, but here again we have just saying that it can be divided by a and b can be divided by 5. So it will be the contradict, you see. But this contradicts the fact that a and b are co-prime. Step 3 I have mentioned. This contradiction has arisen because of our incorrect assumption that root 5 is rational. Hence we conclude that root 5 is irrational number. Now proceed to the question number 2. Prove that 3 plus 2 root 5 is irrational. Let us assume to the contrary that 3 plus 2 root 5 is rational. Therefore 3 plus 2 root 5 equal to a by b, where a and b are co-prime. You just transpose this 3 to this side, so we will get 2 root 5 equal to a by b minus 3, and solve it, a minus 3b by b. Root 5 is equal to a minus 3b by 2b. Now on the right hand side we are getting in the form of fraction, you can say, or in the form of a rational number, because these are the integers. You see, a minus 3b by 2b is a rational because a, b are integers. Once the right hand side is a rational, that indicates that left hand side is rational. Means root 5 is a rational. But this contradicts the fact that root 5 is irrational. It is already proved that root 5 is irrational. This contradiction has arisen because of our incorrect assumption that 3 plus 2 root 5 is rational. This was the incorrect assumption. Hence we conclude that 3 plus 2 root 5 is irrational. Now proceed to the question number 3. Prove that the following are the irrational. First one is, that is 1 upon root 2. Let us assume the contrary, that 1 upon root 2 is a rational. So in step 2 I have put 1 upon root 2 equal to a by b, where a and b are co-prime. So root 2 will be equal to b by a. I have just inverted it. The right hand side, b by a, is a rational number, as b and a are integers. Hence once right hand side is a rational number, so left hand side should also be a rational number. Root 2 is a rational number, whereas root 2 is irrational, already proved. This contradiction has arisen because of our incorrect assumptions that 1 upon root 2 is rational. So we conclude that 1 upon root 2 is irrational. Now, for the second part, prove that 7 root 5 is irrational. So the steps are like this. In the first step, let us assume that 7 root 5 is a rational number, which is a contrary assumption. Therefore, 7 root 5 is equal to a by b. Once we have assumed that it is a rational number, so we can write it. It is equal to a by b. This means that the root 5 is equal to a upon 7b. Now a upon 7b is a rational number as a and b are integers. In step 3, therefore, the root 5 is also a rational number. Root 5 is also a rational. Once we have said that the right hand side is a rational, so the left hand side will be also a rational. So root 5 will be also a rational number. Root 5 is also a rational number, but this contradicts the fact that root 5 is irrational. It is already established that root 5 is irrational. Therefore, in the step 4, this contradiction has arisen because of our incorrect assumption that 7 root 5 is a rational. It is a incorrect. Our incorrect assumption that 7 root 5 is a rational. So we conclude that 7 root 5 is irrational. Now come to the third part. 6 plus root 2. Let us assume to the contrary that 6 plus root 2 is a rational. In step 2, 6 plus root 2 equal to a by b. Once you have assumed that it is a rational, then you can put a by b. So the root 2 will be equal to a upon b minus 6. Further solve it, a minus 6b by b. So root 2 will be equal to a minus 6b by b. Here the right hand side is a rational number because a, b and 6 are the integers. Step 4. From the third step, we get that root 2 is a rational. But this contradicts the fact that root 2 is irrational. It is already established that root 2 is irrational. So hence I have mentioned here, but this contradicts the fact. This contradiction has arisen because of our incorrect assumption that 6 plus root 2 is rational. It was the incorrect assumption. So we conclude that 6 plus root 2 is irrational.